Next up, we have DEIRDRE Connolly, who is with us from Brightcove, who will be talking about getting into security through the standards body process. Welcome.
Oh, sorry. Hi there, my name is DEIRDRE Connolly. I'm a software engineer at Brightcove. And today I want to talk a bit about security standards, elliptic curve cryptography, and how getting involved with these standards bodies can make you a better engineer and make a web scale impact. So to give a little context, a couple of weeks ago, the CFRG, the Crypto Forum Research Group, which is part of the IETF, the Internet Engineering Task Force, submitted a new draft for new elliptic curves to be used in internet security standards such as TLS, the security protocol that secures all of your internet traffic when you're using HTTPS. Before I get into what elliptic curves are and why you care, one thing that's kind of interesting about this very fancy, math-heavy technical document is that somehow my name got in there. And if you had told me 6 months ago, a year ago, that I would have anything to do with a cryptographic document or an internet standard or anything like that, I would have thought you were insane, because I didn't know anything about this until 6 months ago. And if I can get involved with this group and I can get involved with standards bodies, anyone can do it. And the reason you should is because these are the protocols that we use to build internet scale systems, and the security standards that are part of that make all these things work together securely. If you've used banking applications on your phone, in your browser, you are using these standards right now, and it's very possible that you are building systems that use these standards. By getting involved with these standards bodies, you can both learn how they work, learn how these standards get disseminated and implemented by companies around the world, and it really helps you grow as an engineer. And if you really find something that you're interested in, you can make a web scale impact. And so what I'm going to do is I'm going to talk about what the hell are elliptic curves, why do you care, who are the people that make these standards, and how you can get involved and make an impact. So, oh no, this is the other way around. Okay, so first I'm going to talk about standards bodies. So the IETF, the Internet Engineering Task Force, is an independent body that of engineers, domain experts who work together for free, for the most part, to devise technical specifications that define how the internet works. These include things like TCP/IP, HTTP, there's an HTTP working group, and of course TLS, the Transport Layer Security Protocol, originally called Secure Sockets Layer, SSL. Parallel to the IETF, which is comprised of working groups, there's the IRTF, the Internet Research Task Force, which is comprised of groups that do more independent research about protocols and make recommendations to other groups in the IETF. That includes the Crypto Forum Research Group. The Crypto Forum Research Group is cryptographers, technical experts, and random people who join the mailing list and discuss what's going on in the field of cryptography, how it might be applicable to internet standards, and how best to encode that information into a technical document that implementers can then take and build themselves. And the important thing about these internet standards bodies and the documents they produce is that they're independent and available to everyone. So if you have a top-down standards process where everyone has to be in on it, everyone has to agree, and everyone has to make a decision, and it gets sent out to everyone like this is the way you have to do it, it's hard to scale. But these documents are, they're decided upon and they're out there, and then anyone can implement them. So if you're just writing your own implementation of TLS, you can do that. And then it will go work with someone else's implementation of TLS, knock wood, if you design it and build it to the spec. This allows us to design systems at internet scale that can interoperate securely if you both adhere to the protocol outlined in these specification documents. So, okay, cool. So what specifically do we care about, and why am I talking about it today? So if you use secure internet connections, almost always they are encrypted with a shared key. Whether or not that shared key is long-lived depends on what sort of version of the protocol you're running, and it also has an impact about is your traffic secure today, secure tomorrow, and if someone compromises that key, what does that mean? The first few years when we were using TLS, there would be a long-lived key shared amongst multiple users of a server. So if client A connected to connected to Facebook, they might be served the same key as client B. And if someone decided to record your traffic and then compromised your key later, all of the traffic that they had recorded could be decrypted by that key. So this isn't very good. We want something that makes our secure connections safe in the past and in the future. And what we want, that gives us a nice feature called perfect forward secrecy. The way to achieve that is by creating a new key for every session. For every client and server pair, you have a new key for that session. And then as soon as you're done, the key is thrown away. This means that if your traffic is recorded and the key is compromised, it's only good for that session. So anything before that or after that, it's a completely different encryption key, and your traffic is not vulnerable to be compromised. Okay, so how do we do this? Well, the traditional way of agreeing on an ephemeral, a session one-time secret key, is with something called Diffie-Hellman key exchange. This was a breakthrough in asymmetric cryptography that was devised in the 70s. And the primary concept is, for two parties that have never met each other before and have no information about each other, they can exchange information in a clear channel that anyone can see, but still agree on a secret piece of information that only those two parties know about. And when you have that kind of secret information, a shared key, you can then have symmetric encryption between the two of you. And the important thing about this kind of key exchange is it has to be efficient enough to do it every time, or else you can't achieve perfect forward secrecy and you're back to the old way of doing things. Now, the way that this is usually done is there is a common parameter, a common piece of information known to all parties that understand this protocol. And I'm going to explain this with this kind of traditional analogy of mixing paints together. So Alice and Bob pick their secret color, they pick a secret value, mix it with the commonly known value, and this produces their public key. Now, the key part of this sort of analogy is that the mixing together of these values is easy to do in one direction. It's easy to produce that orangey color or that bluey color. It's really hard to figure out the exact values of the two things that went into making that bluey color or that orange color. This is actually a mathematical computation that is considered very hard to do. It's cryptographically secure. So what you do is you swap your public values with the person you want to communicate with, and the other person mixes their secret value again with your public value, and both of you are able to agree on a shared secret. Now, this sounds great, so why don't we just keep doing this forever? Well, we were doing it forever, but at the same time, computation and computers were getting faster, and as computers got faster, the attacks against this sort of cryptographic protocol got easier, and so we had to make bigger keys, and bigger keys over the internet means more bytes that we have to send and more round trips, and it was kind of getting untenable. So in the 80s, a couple of cryptographers started thinking about a better way to do Diffie-Hellman, but not necessarily with raising a number, a common number, to an exponent, your secret key. And they came up with using elliptic curves to do Diffie-Hellman. Now, this is an elliptic curve. Elliptic curves don't have anything to do, well, almost nothing to do with ellipses. They're basically a distant family relation of ellipses, like circles. And the key difference for elliptic curves is that instead of raising a number to a power, and that is the secure computation, you take a point, which is the solution to this equation, and you multiply that by a secret value. And it turns out that this sort of computation is hard to undo. There's a very nice properties about elliptic curves that make undoing this sort of computation difficult. And the big win for elliptic curves is that you can have the same security value as you would, the security level that you would have for a traditional Diffie-Hellman, but it takes 10 times less computation. It takes 10 times less length of a key. It's faster, it's more efficient, and that is really good for achieving perfect forward secrecy. One of the big wins as well is that you don't have to do as much configuration as a server maintainer to set up elliptic curve cryptography. There are some things that you have to set up doing traditional Diffie-Hellman that not everyone was doing correctly, and it became a security vulnerability. And I can tell you more detail about what that was and why the NSA might be taking advantage of it later. So this is a curve that your browser is actually using. And this, if you're using elliptic curve cryptography in your browser, this is the exact curve that it's probably using, called P256. This is a NIST standardized curve. These are very well known. They've been in use for over a decade. This is called a Weierstrass curve. And unfortunately, this is the math you have to be able to do computations on this curve. And you don't have to know what this is, and you don't have to understand it. You just looking at this, I kind of think it's kind of scary. And as a person that doesn't have a math background, I'm a software engineer, but I don't have a math degree, this is kind of scary. And building anything that is supposed to operate on this bothers me. It's hard to implement correctly. There's lots of edge cases you have to be aware of. You have to check all of your inputs, because if you put in the wrong input, you will get an output, but it may not be a good output. And in this sort of context, people have been trying to figure out, are there better ways, safer ways that we can use elliptic curves and make better, safer software? And it turns out in the past 10 years, there's been a new field of research into what's called Edwards curves. It's a different set of elliptic curves that have very nice properties and includes, that's all the math you need to do to be able to compute over Edwards curves. It's very nice. That's a really bad format of my math, but it's a pretty simple computation. The computation applies to any input. There are very few edge cases. As long as you pick your curve right, you use the same computation, you put in an input, it gives you an output. If you give it an invalid input, you can't solve the equation. It's just like you try to divide by 0. It just doesn't work. It is easier to implement. It's faster. It has fewer edge cases. And it's also very useful for signing things. So not just computing Diffie-Hellman, but also for signing a value and proving that you are the one that signed it with your public key and your private key. Great. So in this context, the CFRG, the Crypto Forum Research Group, decided to propose new elliptic curves for recommendations in TLS and other security protocols that would use it. This includes Curve 25519, which has been used in Signal. It's used in iOS. It's used in a lot of applications. It's been pretty battle tested. And then there's another curve that has a much higher security level, but is very similar. It's another Edwards curve. This document specifies how to use these curves for key exchange, how to use them for signing, exactly the formulas and parameters that you need to use to be able to do those operations. And basically, it's already started to be integrated into the new version of TLS and other certificate standards protocols that are being worked on right now. My contribution was I was getting really into elliptic curve crypto at this time, and I heard that this working group was talking exactly about what I was trying to learn about. So I literally joined this mailing list to learn. And in the process, they were working on this draft. And I basically contributed enough editorial contributions to say, I don't understand what this means. Can you make it clear? I'm just a regular old engineer. I don't know anything about this math. Can you make it clear so that I understand it if I ever have to understand what someone else's code means, or if I ever have to fix a bug or implement this myself someday? And apparently, I contributed enough that I got acknowledged in the draft. This is really cool for someone like me who didn't know anything about this to start with. And the lesson is that anyone can do this. If you care or have a passing interest, professional or otherwise, you can join a standards body. You don't even have to join a standards body. You can just jump on a mailing list and ignore half the emails if you want to. But you can get involved. And either you can make a contribution and say you contribute edits to a document, or you can just listen to everything that's being discussed, because it's a great way to learn about how these protocols work, what is being worked on, and what are these sort of cryptographic and security principles that underpin our internet as we work on it and develop it into the future. It's like, okay, so how do you do this? Almost every single working group or research group or standards body has a mailing list. This is the bread and butter of discussing new standards, new protocols, new techniques. I recommend that if you find one that you're interested in, you join the mailing list and just listen for a while. You can listen to what people are actually discussing. If there's a topic that you're interested in but no one else is talking about, you can talk about it, but you may not get a response. And you can kind of get a feel of like the community style and how people talk about things. A lot of these groups also have IRC channels, they have Jabber chat rooms, and a lot of these activities are moving to GitHub. So a lot of these drafts used to be just patches flying across a mailing list, and that's okay. But now there's just a document, like a markdown document in a GitHub repo, and everyone can submit pull requests, they can open an issue. If anything is a little bit longer than a short issue or a short patch, or anything changes a fundamental aspect of the design, it's usually discussed on the mailing list. But my point is, it's getting really easy to contribute. It's using tools that we're familiar with, and there's a low barrier to entry. It's not very scary. These groups are being staffed by smart people, experienced people, and also people who are neither of those things. So it's not very scary. It's actually really fun. And if you have something that you're interested in, maybe it's TLS or secure email or certificates or DNS or any of these things, there's a working group that's discussing these things right now that you can join in on. Some of the examples include TLS, the new certificate transparency standards, the Let's Encrypt free certificates for everyone protocols, and of course there's also the W3C. If you are interested in web application development, there's a whole bunch of standards about building secure web applications, and those are full of working groups too. They work a slightly different way than the IETF, but they're still very open, and you can go contribute there. And I have some links here at the bottom. So, takeaway here is that the standards that drive the internet today drive the security and scalability of our future systems. Getting involved boosts your knowledge and capabilities as an engineer. It's fun, it's a great way to grow, and if you find something that you care about, you can contribute to the future of the internet as we build it. And I think that's a huge win. So, thanks.